Alright folks, today we're going to talk about the electrical power subsystem, or the EPS. Here's our lesson objectives for today. So we're going to understand how this thing operates and what are some available energy sources. Talk about some basic concepts. We're going to calculate the length of time a satellite's in eclipse and in the sun. And using that, we're going to figure out how much solar array power is required, and then how much actual power you're going to get at beginning and end of life. And then finally, we're going to talk about this concept of depth of discharge and how it affects your battery capacity. So first, let's talk about some sources of energy. One of the first and most obvious ones is solar energy, and that comes from the sun, as you might expect. The next one is chemical energy. Comes from batteries, which are things that you should be familiar with, and also fuel cells, which you might not be familiar with, but they're pretty cool. Give it a Google. We use them on the Apollo program. There's some cars that run on fuel cells. And then the last source of energy is nuclear energy, and no, that's not a nuclear reactor like on a submarine. It's this thing called an RTG, a radioisotope thermoelectric generator. Go run that to the bar, maybe get some girls. It's a hunk of plutonium decaying, gives off heat, and we turn that heat into energy. Speaking of, let's talk about the difference between power and energy. As our little light bulb is saying, can I get a what? Power is like in watts, kind of what your light bulbs ask for and need. It's also the product of voltage and current. Energy, on the other hand, is power times time. We're going to use that a lot, and the difference between the two, the key thing to hone in on are the units here. So let's also define this concept of eclipse. Eclipse is just when your spacecraft is in the Earth's shadow. So we got a little diagram here, the sun's rays shining on Earth, and then your spacecraft is rotating around Earth, or orbiting Earth. You might think, well, the spacecraft's just dark when the Earth is dark, but that's not really true. So you can kind of see where our spacecraft is right now. It's about to go into what we call eclipse, but the Earth underneath our satellite right now is dark, and it has been dark already. The time that you spend in an eclipse is directly related to this angle 2 rho. That section of the orbit, that amount of the period of the orbit in seconds, is going to be our time in eclipse. So let's talk about how to calculate that. In order to determine your time in eclipse, you're going to take that angle, 2 rho, and divide it by 360 degrees. If rho is in degrees, which it should be, then you get some percentage of the orbit where you're in eclipse. And you multiply that percent times the period, and then you get the amount of time that you were in eclipse. It's cool. This other equation, though, not on your equation sheet. It's time in the sun, and hopefully this should be obvious to you. The time in the sun is just the period minus time in eclipse, because the time in eclipse plus the time in the sun should be one full period. And then at the bottom we got a little equation for rho. Rho is directly related to the height, the altitude of your orbit, and that's how you're going to calculate it, is using that h right there. Just for your essay, fun fact, here's some different time in eclipses for various orbits. In Leo, 35 to 45 minutes, and you're going to have about 5,500 of these each year. Mio, our time in eclipse is getting close to an hour, but you're only going to have 1,000 of those per year. And in Geo, where your time in eclipse is 70 minutes, you're only actually going to have 90 eclipses per year. So that's kind of cool. Now let's talk about how we figure out how much power is required. So you're going to use that time in sun and time in eclipse, that amount of seconds where you're in the sun or an eclipse. And all you're going to do is multiply it by the amount of power that your spacecraft needs. Now, we broke this up into power payload, P_PL, and power of the bus. So let's say that your payload is a camera, and your camera needs, 300 watts of power. That'll be right there, 300 watts. And then power of the bus, that's going to be a whole bunch of different components. We'll talk through a couple of them, and you've talked about a couple of them already, but things like your communication system, your thermal system, your EPS itself sometimes requires power. All of those individual powers, you'll add them all together, and that'll be the total power for the bus. Again, it should be in watts. So to find energy you need in the sun, you'll multiply that amount of power your spacecraft needs times time in the sun. Same thing for energy in eclipse. And then finally, to figure out how much power your solar arrays are required, that's the REQD, required, to generate, you're going to add these two energies up and divide only by time in the sun. Now, why, you might say, only time in the sun? Well, the thing is, you have to produce all of that energy only while you're in the sun, because once you're in eclipse, you're not making any power anymore, so that would be kind of a bummer. Speaking of, let's talk a little bit about solar panels at the beginning and end of life. So at the beginning of life, you might have a nice solar panel, fresh and shiny, right out the box. At the end of life, you might have had, some micrometeoroid debris, as you can see here, got rocked by a little space junk. Another thing that's going to degrade your solar panels is radiation. So that space environment is harsh, and it's going to degrade the coating such that it's not really transmitting as much energy anymore. Not as many photons are going to hit your solar panel. Point is, this power end of life is going to be less than this power beginning of life, but this number still has to be greater than or equal to what you calculated just now, the solar array required. If this was less than the power solar array required, well, let's talk about margin. Right here, we've got power margin, and the solar array margin is your power at end of life minus how much you're required to have at the beginning of life. Cool. So jump back up here, and I'll show you how to calculate power at the end of life. So first thing you do is calculate how much you're going to have at the beginning of life, and that's just this solar input, which is 1358 watts per meter squared, times the efficiency times the area. You notice how solar input is in watts per meter squared. That's power per area. And if you multiply that times area, then you've got power, which is kind of cool. Second, we can find power at end of life using that power beginning of life number times this degradation factor. So this right here, for my econ majors, or anybody who's recently taken econ, should look familiar. It's just a natural decaying function. You're going to have some degradation in a percent. So if it were 15%, you put 0.15 here. And then a mission life. Keep in mind, mission life is going to be in years, because it's degradation per year. Cool. Final note, after you calculated your margin, if your margin is negative, your solar panels are not actually able to produce the power that your satellite requires, and that would be bad. So, let's talk a little bit about collection and distribution, and a little bit of a broken out flat sat here. You've got your sun on the left, that 1358 watts per meter squared, pumping down on your solar panels. And then, depending on how much square footage, or I guess here, square meterage, anyway, it's going to put out a certain amount of power in watts to your power supply. The power supply will supply the batteries, so that those get charged up while you're in sun, nice and topped off. And then there will be some amount of power that also goes into power conditioning and distribution. And you need to have enough power over here, coming out here, to supply all of those little individual components. So here we're showing 4 parts of your spacecraft. There are more. You'll have some amount of power that goes to your payload. Here's 100 watts. And then the other 3 subsystems they chose were CDHS, AOCS, and thermal, and they require 12, 15, and 5 watts each. So if you were trying to calculate that P payload plus P bus from the beginning, you would add 100 plus 12 plus 15 plus 5. And that's how much power your spacecraft requires. So, last topic for today is depth of discharge. Depth of discharge is how deeply have you discharged your batteries. It is the opposite of what you normally are used to thinking about with a battery. And what I would ask you to do is pull out your handy dandy cell phone or your laptop and take a look at the little percent up in the right hand corner here. So right now, I've discharged mine pretty deeply. My cell phone is telling me I'm at 39%. If I'm at 39%, my depth of discharge is 100 minus 39. So what's that? 61. So depth of discharge, in this case, 61%. And just for your essay, a couple of kind of guidelines for how much you can discharge your batteries, depending if you're in Leo, MEO, or GEO. For your design projects, you guys are all hanging out here in Leo, so your depth of discharge will be capped at 25%. That means you can't discharge your batteries any more than 25%, or else you risk doing a lot of damage or shortening their life less than you would want. You're going to use that depth of discharge to calculate the capacity of your batteries that is required. Again, you get that REQD here, that means required. To find out how much battery capacity you need, you're just going to take the energy in eclipse. Remember, that's energy, it's in watts times seconds, and divide it by the depth of discharge. You'll end up with a battery capacity in watt seconds, which is the same thing as a joule. Oh, by the way. Depth of discharge is a unitless number, it's just a percent. So if it were 25%, you would put in 0.25 right there. And then you can figure out how much battery margin you have, similar to figuring out how much solar panel margin you got. Your battery margin is just how much capacity is available. That means, like, if I chose, these cool lithium-ion batteries that are state-of-the-art and they come from Japan, well, that particular battery I just bought, it comes with, let's just say, 450 watt-seconds of capacity. And I calculated how much was required, and it turns out I need 423 watt-seconds. Well, I'll take that 450, put it in right there, 423, put it in right there, and I'm going to end up with a battery margin of, 27 watt-seconds. Which is good, that's positive, at least. You don't want a negative margin, or else you are out of luck. And that is all I have to say about that.
All right, everybody, we're back. I'm going to talk about the electrical power subsystem right now and work through some math for that. As always, I have last year's homework. Let's just get started. All right, FalconSat X, it's FalconSat 10. Is planned to launch into a circular low Earth orbit with an altitude of 700 kilometers. Oh, that's good to know. H equals 700. Designers estimate that FalconSat X will require 450 watts of continuous power throughout its 3-year lifetime. So let's see. That is going to be the power that the payload needs, plus the power that the bus needs. And they just told us that that is going to be 450 watts. Says the mission life is 3 years. Pretty typical for a FalconSat. Actually, it's a little longer than we usually have. But FalconSat 10 is still beeping after 13 years now. So anyway, calculate the solar panel power required for FalconSat 10. So we abbreviate this PSA rect. PSA required, right? But on your equation sheet, it's PSA rect. So we're in the electrical power area, right here. Of all the, areas of our equation sheet and different topics in the course, this I would say is almost the best designed on the equation sheet to literally walk you through the process cradle to grave. So let's begin. The first thing the equation sheet gives us is this rho value. And remember kind of the, let's see here, we have the sun, we have the earth, we have our satellite in orbit. There's our little FalconSat. He's in the sun, he's in the sun, he's in the sun, he's in the sun, and then soon as he enters eclipse, has to start using battery. Cool. So that's basically what we're going to calculate is, wait, okay, so how big do our solar panels have to be to provide a bunch of power? That comes later. And then, first of all, how much power does the solar panel have to provide over the course of the satellite's life, over the course of its daily operations? That's really what this problem set is about. And you might say, well, hey, weren't we just told that we need 450 watts of power and that's it? Like, isn't that the answer to number one here? And it's not quite the answer to number one. It's part of the problem. We need that much power to be powering the payload and the bus. But the trick is we need that much power during eclipse to be provided by the battery. So when we come out of eclipse, we need the solar panels to actually be a little bit bigger than you might imagine, because we have to not only run the payload and the bus in the sun, we have to charge up the battery for the next time we go into eclipse, right? So we actually need a little bit more solar power capacity than you might initially think. So as much as it might seem like 450 watts is like the instant answer, it's not. It's not. Okay, but let's begin. So if I were to draw from the center of the Earth out to where the satellite exits or enters eclipse, this angle right here is rho, right? It's like the little lowercase p that doesn't quite connect to its tail. We need to find that so we know kind of like how much, depending on how close a satellite is to Earth, you can see like a LEO satellite spends almost half of its time in eclipse because it's so relatively close to the Earth, right? It's barely hovering above the Earth in orbit as it goes around the planet. And then if you're out in GEO or MEO, you spend such a tiny, tiny portion by comparison of your orbit behind the Earth. And there's only actually certain seasons of year, like for geostationary, it'll spend, 5 months out of every 6 essentially in the sun all the time, not even going behind the Earth. Because remember, the Earth is tilted 23.5 degrees with respect to the sun. So really, there's only a couple seasons throughout the year. There's a couple times where GEO satellites will even go behind the Earth. But LEO satellites are a totally different story, right? This is a common occurrence for most orbits that are LEO. So anyway, all that to say, how much, in terms of a fraction of time, do we spend behind the Earth, which means how much time do we need to run on batteries and keep the mission going? That's what rho is going to tell us. And we find it's the inverse sine of R over R plus H. Remember, calculator needs to be in degrees for this. Let's do a little plugging and chugging. We know the radius of the Earth is 6378.137. We were told our satellite's orbital altitude is 700, so we'll add that here. And that should give us, let's see, cool, is about 0.9, so we'll take our inverse sine of that. I get 64.304 degrees. Great. So really the total fraction that it spends in eclipse is twice that angle, right? Because it enters eclipse down here, exits eclipse up here. So really it's that angle times 2. Okay, let's see here. So the next thing we want to find is actually, so this is step 1. Step 2 is to find how long does our satellite actually spend orbiting, just to find the period. And we actually need that. So going all the way back to the other side of the equation sheet, period, woo, all the way back here, 2 pi times a cubed, other than you. And you guys can tell me off the top of your head what A is, sine major axis. Did we find that from the problem stuff that we're given? I think so. Because that would just be the radius of the Earth, 6378.137 plus 700. All that cubed over 39600.5. Make that a little clearer. There's a 3 there. Oh, I didn't make it clear, but okay. So square root of, and let's just do this piecewise. 78.137 plus 700 cubed. Answer times 2 pi. Good, and that gives us, oh, I don't know, about 59.26 seconds or so. 379, you know me, I like to take it all the way up 3 digits. Okay, good. They didn't ask us for that. In fact, all they really want is the PSA required, so we're marching our way down the left side of the equation sheet here in order to do that. Okay. Next step, we want to find time in eclipse. In fact, real quick, if I was going to modify the equation sheet, I would say that right in here is a step where you need to find period, right? That's what we just did. So you go rho, then p, then time in eclipse. Let's find our time in eclipse. Okay, so this is the amount of time as far as seconds go, instead of a fraction. Seconds. How many seconds do we spend in eclipse? If we spend 64 times 2 is about 128-ish degrees out of 360 degrees in shadow, then what does that translate out to as far as seconds, a fraction of the orbit? Well, let's see. The TE equation, they say, is 2 times rho over 360 degrees, because we get one orbit, 360 degrees, times period, which we just found. So 2 times 64.304 degrees, 360 degrees, times period, 926.379. And that should give us, let's see, 2 times 360. Good, and that gives us that we spend about 2100 seconds in eclipse every orbit. Boo. Okay, so we're going to need some kind of a battery, some kind of a powerful battery probably. Okay, next thing we want to find, let's just keep moving down. Let's find the energy that we use when we're in eclipse. So in that 2100-ish seconds, how much juice do we use? Equation sheet is kind enough to walk us through this. That power of the payload, power that we're using with the payload. FalconSat 10, has multiple different little payloads on it that are doing experiments and all kinds of different information gathering missions scientifically, just to try and gather data. So all those require some power to run. So that's the power used by the payload, and of course the power used by the bus. That's the thermal control subsystem and the comm subsystem and the pointing subsystem and all the other subsystems that need juice, but they're part of the bus. The problem tells us that the total amount, it doesn't break it out into payload and bus, but it does say the amount that's used by both of them all the time is 450 watts. And the equation sheet tells us to multiply that by the time of eclipse we just found. So that's 450 watts times time of eclipse, which what we want to do here is actually convert our time in eclipse from seconds to hours, because we're going to use watt hours for the rest of the equation, or the rest of the equation and the problem. So multiply this by, rather divide it by 3600, 0.588 hours. So that's what we're going to plug in here, 0.588 hours. So the energy we use in eclipse is 264.635 watt, dotted with hours, watt hours. Okay, now let's find the amount of energy we need in the sun to both run the payload in the bus and recharge the battery from when it was being used in eclipse. That's the next thing we need to find. We're just marching down the equation sheet here. Energy in the sun, energy needed to both power the battery and the bus and the payload in the sun. So we're going to take that power sub payload power sub bus. We're going to multiply that by time in the sun. Now, what's time in the sun? Well, if the total period is either spent in sun or eclipse, that means it can only be one or the other, right? So our time in the sun plus our time in the eclipse is our entire period, right? It's either behind here, it's in eclipse, or it's out in the sun. So that means that I can find the time in the sun just by subtracting time in eclipse, which we already know, from the period, which we already know. And I'll plug that in right here. Okay, so time in the sun, so that's equal, let's see, 450 times, let's see, I'll do it in seconds even. Well, no. Let's convert power, or sorry, the period in hours. Convert the period in seconds to hours. Excuse me. Okay. We'll divide 6.379 over 3600. So in hours, that would be is that right? Sure. 1.5 hours. That makes sense, actually. 1.646 hours. So anyway, going back down here, total period in hours, 646 minus time we spend in eclipse, which we found in hours was 0.588. We're going to get another value of watt hours here. So I find that we need about 476.152 watt hours while we're in the sun, because we've got to collect enough to charge the battery. I can't repeat that enough. We have to, in eclipse, you just have to use the battery to go ahead and power the payload in the bus. In sun, you have the added burden of needing to go ahead and also charge up the battery enough by the time you get to the next eclipse. So that's an important consideration. There are satellites out there that have failed, their solar panels or part of their batteries have failed, so like let me back up. There are satellites out there who have not been able to provide enough power because they've been pointed the wrong way when they're in the sun. And so by the time they enter eclipse, their battery is almost drained and it's not enough to get it through eclipse, and those satellites never wake up on the other side of the eclipse. So, boo, that's never good. So this kind of math is designed to prevent that. So, let's see. Cool. All right, so step 6 here is, I would say, the last step. Look at all these little steps, but they're all little and they're easy. PSA rect. Power needed by the solar arrays or required by the solar arrays is energy that we have to use in eclipse plus the energy we use in the sun, all divided by the time we spend in the sun, right? Because we can only charge our solar panels in the sun. So we found that the energy we use in eclipse is 264.635 watt hours, and the energy we use in the sun is 476.152 watt hours. Time in the sun, in terms of hours, 1.646 minus 0.588. 635. 1.646 minus 0.889. Cool. And I end up getting around 777 watts. Ta-da! We did it! The answer key has it slightly different, 700.10 something. I didn't program, as you guys were watching with me here, I was just calculating this all based on one step, then the next step, and the next step. So that's, of course, a way you can introduce some rounding errors, but again, if you're super close on the GR, we are not going to take points away. Rounding errors happen, even when you carry 3 significant digits like I do. Cool, so that's how much power the solar array has to provide so it can both charge the batteries in eclipse, or charge the batteries in the sun so they can be used in eclipse. Man, today is not a talking day for me. But we will press ahead. Okay, next problem. Okay. FalconSat X will use experimental lighted up, quotes, lighted up solar panels. I looked that up. I'm not sure it's a real thing, but it sounds cool. We should start that business. Myself and all 400 Astro students. No, I'm just kidding. But FalconSat 10 will use experimental lighted up solar panels which have an efficiency of 0.35 or 35%. How large does the effective area of a lighted up solar panel have to be to provide a minimum of 1,500 watts of power to FalconSat X throughout its 3-year mission? Assume the solar panel degrades at 2.5% per year. Okay. Here we arrive at something that's kind of counterintuitive. And what I mean by that specifically is that to figure out what we need to build the satellite's solar panels for at the beginning of life, which is this P sub BOL on the equation sheet, we have to find out what it needs by the end of its life, right? So after the solar panels have spent several years in space, degrading, possibly getting hit by tiny micrometeoroids or space junk, the performance of a solar panel degrades, and it becomes worse and worse over time. So basically, by the end of after spending years in space getting degraded, it still has to provide 1,500 watts of power. So the question becomes, what did it need to provide at the beginning of life so that by the end of its lifespan, after all that abuse, it's still putting out 1,500 watts? Arguably something more than 1,500, right? So that by the time it's done with all that abuse, it's still putting out 1,500 watts. Okay, so the way we do that is the problem told us what we need, how much power we need at the end of life. That's 1,500 watts. And our equation sheet tells us that that's the power that we need at the beginning of the life of the satellite, rather not the power we need, but the power that's generated by the solar panels, is 1 minus the dg of the array. That's one, it's one variable. I want you guys to understand that dg is degradation. Don't know why we just don't call it d, maybe that would be diameter, I don't know. But dg sub array is one variable. Raise that whole thing to the power of the mission life in years. That's what this equation is meant for. So let's do it. Okay. Oops, I don't want to write equals yet. So like I said, we need to find out the power at the beginning of life so that we can find the effective area that we're going to have to build these solar panels to. Like what size do we need them so that they produce a certain amount at the beginning of life, and that amount equates to the degradation over all that time to produce the end of life power which they gave us. So we're really like going all the way backwards through this process. And that's okay. I'm just going to solve for the power at end of life. 1 minus, now degradation is given in a percent, but you need it in a decimal. And 2.5 in a decimal form is 0.025. 5%, I should say, of decimal form. And then we're going to raise that to the mission life of 3 years. Power end of life, 1,500 over 0.025 to the cubed. So this tells us we need 1618 3, 6, 8 watts at the beginning of life of the satellite. So they have to produce at least 1,600 so that by the end of its 3-year lifespan, it still puts out at least 1,500 watts. Okay, so now the question was how big do these have to be? Well, why don't we plug that in? Let's look at the power beginning of life equation. That's the next step. So here's your first step. Here's your second step. Power beginning of life is the solar input times the efficiency of the solar panels times its effective area that we would like to find. So again, I'm just going to solve for the effective area first. So power at beginning of life we found 1618. 3, 6, 8 over. Now, solar input. This is given to you on your equation sheet and it's basically you're getting 358 watts per meter squared while you're in the sun. And the efficiency of the solar panels, again, this little thing is called eta. It's like an N with a long tail. And efficiency, and it's given in percentage, is 35%. We need to convert that to a decimal. Good. That means that no matter how we shape them, they can be a circle, they can be any old shape. They have to be at least 3.405 square meters to produce enough power at the beginning of the life of the satellite. Cool. Satellite solar panels take a lot of abuse, so we do have to plan for them to fall apart over time. Okay, let's see. Question 3 says FalconSat 10 plans on using the Zapit battery, which I feel it sounds like a cheap brand of battery, but that's not real either. Just we love to make up company names, but Zapit plans on using the Zapit battery, which has an advertised capacity of 2,500 watt hours and a depth of discharge of 25%. Calculate the battery capacity margin for FalconSat 10. Okay. Well, we only have one equation we really have to use for this, which is nice, and it's right here, the capacity of the battery that we need. How big a battery? That's the question. How big a battery do we need so that we can only use 25% of it in eclipse and then just charge up that 25% when we come out of eclipse? So depth of discharge is how much of the battery you use. Basically, you only want to discharge 25% of it. Let me put it this way. If we had a depth of discharge of like 80%, that means we would be using the 80% of the battery every time we were in eclipse. It doesn't give you much margin. It doesn't give you much extra. Like, what if you came out of eclipse and your solar panels, for some reason, weren't putting out as much power as you wanted? Maybe you were pointed the wrong way or something like that. You have to use your battery more. And, well, it would sure be nice to have a little more than just 20% left over. That's my example to you. So what we're saying is we're actually going to need a much bigger battery. So if we just discharge at 25%, 25% of whatever battery we choose is going to power us in eclipse. That's our design constraint here. That's what we want. We want to give ourselves like 75% extra margin in eclipse and in sun. Anyway, so let's just crank through the math. Capacity, oh, 1P, why did I do that? Capacity of the battery that we require, bat rect, is energy we use in eclipse. Oh, we found that before, that's nice. Over the depth of discharge. As a decimal, right? We keep converting all these things we need to. Okay, so the energy we use in eclipse, we had it at approximately 264.635 watt hours over 0.25, and that gives us cool. We actually need a battery that can pump out almost more than 1,000 watt hours if we're going to try and plan for a situation where we only use 25% of it in eclipse, which is a good way to plan. So, all right, so that's the actual capacity of the battery that we need. That's not what it says, though. It says calculate the margins for FalconSat 10. So this is not on your equation sheet. Again, margin is just how much you have versus how much you need. How much you have versus how much you need. So the margin in terms of watt hours, if FalconSat plans on using this big old Zapit battery that has an advertised capacity of 2,500 watt hours, so that's how much we're actually going to, that's the battery we're going to use on the satellite. So we're going to use 2,500 watt hours. The capacity of the battery that we actually need is 1058.4 watt hours. So that means we have 1441.46 watt hours left over. So that's the actual margin. And the margin as a percentage, it didn't ask for this, but I'm just going to do the calculation, is margin as a percent is what you just found is left over. Oops. Divided by the total that you have available to you. So 0.5. 7658 equals 57.658%. Again, probably didn't ask for it as a percentage. It said find the margin, which is that. So we did it with, and even did a little more. So, all right, that was fun. Solar panels are cool. Batteries are cool. They're both necessary for spacecraft operation. Talk to you guys next time.